Yes.
Can everybody? Yeah.
Yes.
Okay.
Being recorded.
Okay. So in the proof, some people wanted some additional information about this proof. So I'll start with that. So you see, we had this A module E, and then from E, we got a K vector space, where K is A modulo this maximal ideal. And what is the K vector space? It's E modulo ME, right? That has been given a K vector space structure. And the claim was that if I start with the basis of E, this E iota, then their images, E iota bar, they form a basis of the K vector space E modulo ME. And here's the proof. So they obviously generate this space because these E iotas generate the space, the module E. So all you need to show is that these E iota bar are a free family. Okay? In order to show that it's a free family, you have to show that whenever there's a linear relation, all the coefficients are 0. Okay? So suppose I have a linear relation, excuse me, A iota bar, E iota bar, sum over iota in I, and that sum is equal to 0. Then this expression is the image of this expression, sum over iota in I of A iota, E iota. And being equal to 0 means that this expression belongs to ME, because ME is the kernel of the map from E to E modulo ME, right? So we have this in the kernel. Now, by definition, what is ME? It is the set of all linear combinations of elements of the type B lambda X lambda, where B lambda is in M and X lambda is in E. So this element here, which is in ME, can be written as the sum over lambda in L, where L is some finite set of B lambda X lambda, where B lambda is in M and X lambda is in E. Okay. Now these X lambdas are in E, and I have a basis of E. This E lambda, well, it should not have been E lambda, it should have been E iota. These E iotas form a basis of E, and X lambda is one particular element of E. So I can write X lambda as a linear combination of these E iotas. So when I do that and expand, I'll get the right hand side will be a linear combination of the E iotas with the coefficients C iotas, which will be in M. Why are these coefficients in M? Because they are all multiples of B lambdas, which are in M. Okay. So these coefficients are in M, and I get this relation, right? This expression equal to this expression. Alpha iotas, the coefficients here are alpha iotas, and the coefficients here are C iotas. But the family E iota is free, which means that alpha iota must be equal to C iota for every iota. But C iotas were in M, whereas A iotas, I want to prove that their image in E modulo E, in A modulo M is 0. That is now proved because these C iotas are in M. So therefore this A iota bar is equal to 0, and this family is free. So that was the proof which I sort of skipped yesterday, and it's good that somebody asked so that I could do it today. Now I will quit this thing and go to the other other set of slides. Here it is. So it starts on page 61, right? Can you see it now?
Yes.
Yeah, okay.
Yes, sir. Yes.
Okay. Rahul, does that answer your question?
Yes, sir.
Okay.
So thank you so much, sir.
Right. So today we are going to start discussing integral rings and principal rings and modules over principal rings, finitely generated modules over principal rings. So we have to start with some basics about this kind of integrals and so on. And there's no harm in recollecting this basic material. So let's start with the definition. What is an integral ring? Sometimes people call it an integral domain, but I just call it an integral ring because it's a ring which is integral. What does it mean for a ring to be integral? It should be, first of all, commutative. It should be different from zero. And the most important property is that whenever the product of two elements is zero, one of them has to be zero. That is a property, doesn't hold in every ring. For example, if you take Z modulo 6Z, right? Then 2 times 3 is 0, but 2 is not 0 and 3 is not 0 in that ring, right? So one basic example of integral rings is provided by subrings of commutative fields. For example, if you take any subring of Q, that ring is going to be integral. Z is just one example of a subring of Q. There are many others. They are all integral. Conversely, we could ask, does every integral ring arise as the subring of some field? And the answer is yes. Every integral ring can be viewed as the subring of some field, and there is a field actually which is minimal for this property. And here is the precise formulation of this statement. It says, if you take any integral ring A, then there is an injective homomorphism J from A to K into a field K, which is the following universal property. So given any injective homomorphism F from A to some field capital F, there is a unique homomorphism of fields G from K to F, which makes this triangle commute. So that F is obtained as the composition of J and G. Okay? So this construction is actually a generalization of the passage from Z to Q. How does one construct the field Q from the ring Z? You do exactly the same thing in general. So let's go over it briefly. You take N to be the set of non-zero elements of the ring. It's not empty. It contains 1, for example. And it's actually a monoid because the ring A is integral, which just means that it contains the product of any two elements it contains. And on the set A cross N, we define an equivalence relation. So two pairs A1, B1, a pair A1, B1 is going to be equivalent to a pair A2, B2 if A1, B2 is equal to A2, B1. And so this is obviously an equivalence relation. And the equivalence class, it's called tilde. The equivalence relation, the name of the equivalence relation is tilde here. And the equivalence classes for this relation, the equivalence class of the pair A comma B is going to be denoted by A slash or A over B, like this. So for the time being, it's just the set of equivalence classes. We are now going to make it into a ring. So you have to define how to add two elements, A, B plus C, D. You define it to be AD plus BC, BD, and the product is just the product of AC, BD. You can check that this definition is compatible with the equivalence relation tilde. What does that mean? It means that if I replace AB by some pair which is equivalent to AB, let's say A prime, B prime, and then I take the sum, I replace CD also by some pair C prime, D prime, which is equivalent to CD, then here I'll get A prime, D prime plus B prime, C prime, B prime, D prime. The claim is that that new expression is going to be equivalent to AD plus BC, BD. That's what it means for the addition to be compatible with this equivalence relation, and the same holds for this multiplication. So, which means that I now have an equivalence, I now have an addition and multiplication on the set of equivalence classes. Let's call K the set of equivalence classes. It has an addition and a multiplication, and the zero element is 0 upon 1, and the unit is 1 upon 1. So with these four things, it becomes a ring. Of course, it needs to be checked. Some small checkings need to be done. But it's a field in this, because if I take any non-zero element A upon B, it just means that A is not zero. Then it has an inverse. The inverse is B upon A, and I can talk of B upon A because A is not zero. So this construction, you have done it for rational numbers, and I have this mapping, from A to K, which takes every x to x upon 1. It's injective, and so homomorphism of rings. Now this was a construction of the field K. This field is called the field of fractions of the integral ring A. Now we are going to prove the universal property of this pair K and the injection J. So I'm given a homomorphism, injective homomorphism of rings from A to F, where F is a field, and I have to prove that there's a homomorphism of fields, let G from K to F, which makes this triangle commute. So you define G of an equivalence class A over B to be F of A. F of A makes sense because A is an element of A and F is defined on A. F of A times F of B inverse. F of B also makes sense because B is non-zero and F is injective. So F of B is also non-zero. And the inverse exists because this capital F is a field. But the definition has to be shown to be independent of the choices we have made, and the choices that of representatives A and B. In other words, if I have to check that if A upon B is equal to C upon D, then this FA, FB inverse is equal to FC, FD inverse. And here is the checking. The last line is the checking. If A upon B is equal to C upon D, then AD is equal to BC. That's by definition. Then F of AD is going to be equal to F of BC, right? If these two elements are the same, the images are the same under any map. But F of AD is going to be F of A times F of D, because that's F is a homomorphism of rings, and F of BC is going to be F of B times F of C. So I multiply by FB inverse and FD inverse on both sides to get this relation which I want. So that shows the existence of this map G. Okay. Now, over this kind of integral rings, we can talk about modules which are torsion modules. What are these things? First, we define an element of a module to be a torsion element if it's not free. That's very simple as a definition. So, if you go back to what it means for an element to be free, not free means that there's an alpha which is not zero, but alpha times x is zero. That's what it means for an element x to be torsion. There's an alpha different from zero in the ring such that alpha times x is equal to zero. For example, zero is always a torsion element. And we denote the set of torsional elements of E. I mean, well, this module is sometimes being called M and sometimes being called E. But okay, the torsion element, the set of torsion elements of a module E will be called T of E. Okay. And this statement here says that T of E is actually a submodule of E. Okay. So what do I have to show in order to say that it's a submodule? I have to show that if it contains two elements, then it contains all linear combinations of those two elements. So let's start with two elements x and y in T of E. Because they are torsion elements, there exist elements alpha, beta different from zero, such that alpha of x is zero and beta of y is zero. Because this ring A is integral, alpha beta is non-zero. And because it's commutative, for every lambda and mu, I'll have alpha beta times lambda x plus mu y is going to be zero. So that shows that lambda x plus mu y, this linear combination of x and y, is also a torsion element. And that's so this T of E is a submodule of E. Now, here's another fact. If I have an integral ring A and a linear map U from E to F, then it says little a that it takes the torsion subgroup into the torsion subgroup. That's kind of completely obvious. The second one says that if this map U is injective, then the torsion subgroup of U, the U takes the torsion subgroup of E to the intersection of the torsion subgroup of F with the image of E. And this is also kind of more or less obvious. This third thing, little c, requires a proof, and we are going to give it here. It says that if U is surjective, and the kernel of U is contained in the torsion subgroup of E, then the image of the torsion subgroup of E is equal to the torsion subgroup of F. Okay? So let's first prove that the restriction of U to the torsion subgroups is surjective. So we start with an element Y in the torsion subgroup of F. Because the map U is surjective, Y is equal to U of X for some X in E. I want to be able to find an X in T of E, but all I can do for the time being is that there's an X in E of which this Y is the image. Y is equal to U of X. Okay, so there's an alpha, non-zero alpha in A such that alpha of Y is zero. That's because Y is a torsion element. What is U of alpha X? That's zero because it's alpha of Y and that is zero. So this alpha of X is in the kernel of U. but the kernel of U is contained in the torsion subgroup of E. Okay, so there's an element beta, non-zero element beta in A, such that beta of alpha x is equal to 0, right? Because this alpha x belongs to the torsion subgroup, so there's a non-zero beta such that beta times alpha of x is 0. Now this ring A is integral, so alpha beta is not 0. Alpha beta is not 0, so this x is actually itself a torsion element. So the torsion subgroup of F is contained in the image of the torsion subgroup of E. And the other direction is already clear from this little a. So we get this little c as well. Okay. Okay. Now, is there a question or? Okay. Sorry. Now there's this very important notion of divisibility in integral rings. We are familiar with this notion in the ring Z of integers, but this is something which is, or something analogous is there in every integral ring. It will not have all the properties that hold for the divisibility relation in the ring of ordinary integers, but there are quite a few things which make sense. So let's start with this general integral ring A, and I'll denote by A not 0, A sub not 0, take the set of all non-zero elements of A, so that I don't have to repeat every time x in A such that x is not 0. I simply need to say x in A not 0. And because the ring A is integral, this is a submonoid, right, of the multiplicative monoid. The product of any two non-zero elements is non-zero, and 1 is there because the ring A is not the zero ring. Inside this A not 0, I have the subgroup of integral of invertible elements. Okay, and I'm going to use this abbreviation A heart, A sub heart. You know, this little thing here is supposed to represent the heart. This is my notation for this lecture. It's not standard at all, but it will make many statements very convenient. You know, it's a very convenient notation which I've just adopted for this these notes. So A heart is the set of non-zero elements, but you remove the units from that the set of non-zero elements. You remove the units. So it's A heart, an element is in A heart if it is non-zero and non-unit. Now, if this A is actually a field, then this A heart is going to be empty. It's if and only if. Because the field is one in which every non-zero element is invertible. So that's it. Now, two elements x and y of the ring A, I say that x divides y, or x is a factor of y, or x is a divisor of y, if or y is a multiple of x, if the ideal AY is contained in the ideal AX. You see, if x divides y, we are used to thinking of x as being in some sense smaller than y. But the ideal AX is actually bigger than the ideal AY. The sort of, it gets reversed. And I'll write A, the x is sort of equivalent to y up to units. This is the notation, tilde with A star in the subscript. If AX is equal to AY, these two ideals are equal. And I also say that x and y are associates if they are equivalent in this sense. So this is obviously an equivalence relation, and we will say that x is irreducible. That's the concept which we are which is very basic. An element X in A is going to be called irreducible if it is, first of all, in A heart, which just means that it should not be 0, it should not be invertible. And the only divisors of X are units and associates of X. Of course, every unit is a divisor of every element, because the unit generates the unit ideal. Unit ideal is the whole ring, and every ideal is contained in that unit ideal. So a unit is another name for an invertible element. A unit always divides every element of the ring. And of course, all associates of X will also divide X, because right, X is a multiple of its associate. If the associate is U times X, then X is U inverse times U of X. U is a unit, so it has an inverse. Okay, so that's one definition. And another definition is that of a prime ideal in a ring. Earlier we had discussed what maximal ideals are. They are ideals such that modulo which the quotient is a field. Now we come to prime ideals. These are ideals modulo which the ring is integral. Okay, modulo which the quotient is integral. So although A itself is integral, not every quotient not A modulo I doesn't need to be integral. I mean, this is already clear for A equal to Z, where Z modulo 6Z, for example, is not an integral ring. You can check that Z modulo NZ is integral if and only if this N is a prime number. And another thing which you can check as an exercise is that if I have a finite ring which is integral, then it's actually a field. Anyway, so let's come back to these irreducible elements and prime ideals. Okay, these are two notions which we introduced. And the first statement here says that if a non-zero element X generates a prime ideal, then this element has to be irreducible. Okay. Now, here is a proof. So I have to prove that it's irreducible. So let's start with the factorization. I mean, we are going to prove it by contradiction. So assume that X has a factorization A times B. And the images of A and B in A modulo AX are A bar, B bar. So if X is equal to AB, then X is, of course, 0 in the quotient. So A bar, B bar is going to be 0. But by hypothesis, AX is a prime ideal. So A modulo AX is an integral ring. And the product of these two elements is 0. So one of them has to be 0. So A bar is 0 or B bar is 0. Now, if A bar is 0, it means that A belongs to AX. And actually, you will see that you have equality here, right? So you have either A is equal to the whole ideal, or B generates the whole ideal. And therefore, you have this lemma. Okay. Now let's come to these principal rings. These are integral rings in which every ideal is principal. And when is an ideal B in a ring called by a single element? Okay. So, for example, in the ring Z of integers, every ideal is principal, because every ideal is the form nz for some integer n. Similarly, if you take some field little k and take the polynomial ring, that also is a principal ring. Again, these rings are sometimes called principal ideal domains. But I prefer this shorter terminology because they are rings in which every ideal is principal. So I call them principal rings. So the definition is that every ideal should be principal. Now, you are familiar with this notion of the GCD, or the greatest common divisor of two integers. This notion doesn't make sense, or I mean, the GCD of two elements need not always exist in an integral ring. But if the ring is principal, then the GCD always exists. Anyway, so you just define, in the case of principal ring, the GCD of two elements x and y to be, you look at this ideal ax plus ay. Ax is an ideal, ay is an ideal, their sum is therefore an ideal, right? So this ideal has to be principal because every ideal in A is principal. And any generator of this ideal is called a GCD of x and y. So here one doesn't talk of the GCD, but one talks of a GCD. And you say that x and y are relatively prime if their GCD is a unit. Okay? So that amounts to saying that ax plus ay is equal to the whole ring A. Okay, so here is a small proposition which says that if A divides the product of two elements, and if A is prime to B, if A divides BC and A is prime to B, then A has to divide C. Okay? So I'm translating these two conditions. A divides BC and the GCD of A and B is equal to 1. The GCD of A and B is equal to 1 means that there exist x and y in my ring A, such that ax plus by is equal to 1. Right? That was the definition. Ax plus ay should be equal to the whole ring A, which means that there is an x and a y such that ax plus by is equal to 1. Also, BC is a multiple of A, so BC is equal to AD for some D in A. Now I have to show that A divides C, right? That was the conclusion. So I can write C as 1 times C, and this 1 has been rewritten as ax plus by. So now you expand it and you see that it's, you can express this thing as a multiple of A. So C has to be divisible by A. Okay, so the next assertion is that in a principal ring, the following notions are equivalent. An element being irreducible, the ideal generated by that element being a non-zero prime ideal, and the third thing is that the ideal generated by that element is a non-zero maximal ideal. These three notions are equivalent. They're not equivalent in general, but in a principal ring, they are equivalent. So let's see. If it's maximal, then of course it's certainly, if AX is a non-zero maximal ideal, then it's certainly a non-zero prime ideal, because every field is after all an integral ring. And we have already seen that if it's a prime ideal, then this element X is irreducible. That we had already proved here. If X is a prime ideal, non-zero prime ideal, then X is an irreducible element. So it suffices to prove that A implies C. Okay, so we assume that X is irreducible, and I have to show that AX is a maximal ideal. So let's take some ideal between AX and A in order to get some contradiction. That the ideal between Ax and A will have to be principal, just as all ideals in A. So let's call it AY. So if Ax is contained in AY, it means that X is a multiple of Y. So write X as A times Y for some A. But this X is irreducible by hypothesis. So either A is a unit, in which case this Ax is going to be equal to Ay. If A is a unit, I mean, these two ideals will be the same, or Y is invertible. If Y is invertible, then your then your ideal is going to be the whole ring A. So we have seen that if some ideal is there between Ax and A, then it has to be either equal to Ax or equal to A, the whole of A, and therefore Ax is a maximal ideal. Okay. Now, there's this important property of principal rings, which I need, and it says that principal rings are factorial. So let me define what it means for a ring to be factorial. So I'll do it in the next slide, but here I'm proving some preliminary statements. So the first one says that if a ring A is principal, then every X has an irreducible factor. Every X which is in A heart. And A heart, remember, is a set of non-zero, non-invertible elements of A. So that has an irreducible factor. Okay? So here's the proof. Let's put X naught equal to X. If X naught is irreducible, then there's nothing to prove. I mean, X naught is a factor of itself, right? So if it is not irreducible, then we can always find an X1 in A heart such that Ax naught is strictly contained in Ax1. X1 is a strict divisor of X naught. Okay, if X1 is irreducible, we are done. Otherwise, we can find an X2 in A heart such that Ax1 is strictly contained in Ax2. Same as before. So we will get a sequence of strict inclusions of ideals, strictly increasing sequence of ideals, Ax naught contained in Ax1, contained in Ax2, and so on. I claim that this cannot happen. This has to terminate at some point. In order to show that, let's look at the union of all these ideals. Suppose it goes on, and let's look at the union. And that union is, of course, an ideal of the ring A. And as every ideal in the ring, it has to be principal. So if it's AY for some Y, then there'll be some index to which this Y belongs. But then this inclusion of AXN in AXN plus 1 cannot be strict. That's a contradiction. We are assuming that there's a strictly increasing sequence of principal ideals. And the contradiction is that their union is also a principal ideal, and that will have to occur somewhere in the sequence, because any generator occurs somewhere in the sequence. Okay, so that shows that in a principal ring, every element in A heart has an irreducible factor. So the next statement is that in a principal ring, every non-zero element is actually a product of irreducible elements. Okay? So for the timing, we just know that it has just one irreducible factor. It has at least one irreducible factor. Now we are going to show that it's actually equal to a product of irreducible elements. So if this x naught, which is given to you, is a unit, then it's the empty product. It's it's equal to a product of irreducible elements up to associates, right? So by definition or by convention, the empty product is always equal to 1, and your unit, any unit, is associated to the element 1. So that case is taken care of. So if it's not an invertible, then it has to be in A heart. And we know that every element in A heart has at least one irreducible factor. So let P1 be an irreducible factor of x naught. Then you look at x1, which is equal to x naught divided by P1. Yeah? P1 is a factor of x naught. So when you divide, you get an element of A. If that element x1 belongs to A star, we are done. Because x naught is going to be the product of, is just going to be equal to P1. Up to a unit. Okay. Otherwise, this inclusion of AX naught in AX1 is going to be strict. So you repeat the argument which we had done here. This will have, this X1 will have an irreducible factor P2, and if P2 is a unit, we are done. Otherwise, we get this strict inclusion. And this process of strictly increasing principal ideals will have to terminate, just as before, because the union has to be a principal ideal, and any generator of that principal ideal will be contained in one of the ideals in the sequence. And from then onwards, it will have to be equalities and not strict inclusions. So that contradiction shows that this process terminates, and every element, non-zero element of the ring is the product of irreducible elements. Okay. Right. Anyway, so now this one shows that this is the one where I proved that a principal ring is actually a factorial ring. What does it mean for a ring to be factorial? It means the following. So I take an integral ring A and I denote by K the field of fractions of A, and I let P be a set of irreducible elements of A, not the set of all irreducible elements of A, but a system of representatives up to associates, here. So, for example, if A were Z, then both 2 and minus 2 are irreducible elements in this sense, but I just take one of them. I don't take both of them. 2 and minus 2 are associates. So for each equivalence class of irreducible elements up to associates, I take just one irreducible element. That's the set P. There are various ways of choosing P, but you make some choice. And of course, it's a subset of K star. K star is the group of invertible elements in the field K. A star is a subgroup. So I can take this quotient K star modulo A star, and P maps to this quotient. And let's call P bar the image of P. Okay. So of course, P going to P bar, this map is bijective by hypothesis. Okay. So that this definition makes sense for an integral ring, any integral ring whatsoever. And I call this ring a factorial if P bar is a Z basis of this K star modulo A star. K star modulo A star is a commutative group. This P bar is a subset if that happens to be a basis of this Z module, then I call the ring factorial. Okay, so this concept should be clear. Of course, it can be translated back in terms of being able to write elements of so here we had expressed every non-zero element of A as a product of irreducible elements. So being factorial basically means that this representation as a product is essentially unique. Essentially means up to the order in which you are writing those factors, it's unique. So that's a bit like the Jordan-Hölder theorem, where we had two composition series, and the claim was that the successive quotients are essentially the same, which meant that they are the same up to permutation. Similarly here, when you write a non-zero element as a product of irreducible elements, you can ask whether you can do it in just one way or many different ways. Essentially, one way is what happens in a principal ring or in rings which are factorial in general. That's the definition of factorial ring. And the proposition is that every principal ring is factorial. Okay, so let's prove this. What we already know for principal rings, that P bar generates K star modulo A star. This is just saying that every element of A is a product of irreducible elements. This is just a consequence of that thing. So what we need to show is that this P bar is a free subset of K star modulo A star. In other words, if you translate it back in terms of A, then it means that if I have two families of integers, natural numbers, they should be, of natural numbers, MP and NP, indexed by P's in this capital P, which is my set of representatives of irreducible elements. And and these two families have finite support, meaning all these elements are actually equal to 0, then I can take the product of all elements in the product over P in P of P to the power MP. And similarly, I can take the product of these P to the power NPs. And if these two products turn out to be associates, then these two families have to be the same. That is what it means for the ring to be factorial, for this P bar to be free. It's a translation which one has to make. We already know what it means for a family of elements in a module to be free. You translate that, here the module is K star modulo A star. You translate back this notion of P bar being free in terms of the ring A, and that's what it amounts to. It says that if I take two families, M and N of finite support, and I look at these two products, if they happen to be associates, then M and N are the same. That's what it amounts to. So that's what we need to prove. Okay. If they are not the same, there's going to be some Q in P such that MQ is smaller than NQ. I mean, up to changing M and N, we can assume that there is some Q in P such that MQ is strictly smaller than NQ. Now you can divide both sides of this. This is not an equality, which is equality up to a unit, but you can divide both sides of this relation by Q to the power MQ. Then on the left hand side, there will be no Q anymore. There's no q. Whereas on the right-hand side, you'll get q to the power nq minus nq and the other factors which don't involve q. So by our hypothesis, nq minus nq is strictly positive. So q divides the right-hand side. Q divides this side. So q has to divide this left-hand side. Remember, it doesn't divide any of the factors because all these factors are irreducibles which are different from this irreducible q. So this product of these things is 0, whereas none of the factors is congruent to 0 in the quotient modulo q. And remember, q being an irreducible element generates a maximal ideal. So how can a product of factors which are not 0 be equal to 0? Huh? It means that AQ is not a prime ideal, but that implies that AQ is not irreducible because we had proved that irreducible elements generate prime ideals. Indeed, maximal ideals in principal rings. So this contradiction proves that this family is free and therefore the ring A is factorial. Okay. So I've been very slow today. Maybe I'll take up some of the things tomorrow. So let us prove some small things about these canonical isomorphisms which we'll need later. So I have a principal ring A, two elements D and E in A, and I denote by G the GCD of D and E. Then I have A modulo E and A modulo E, and I have the multiplication by D map from A modulo E to A modulo E. And one can ask, what is the kernel of this map? A going to A modulo E, then you take multiplication by this D. And the image, of course, is going to be dA modulo EA. Or it's D times A modulo EA. It's not, yeah, I should have maybe put parentheses here because it's not dA modulo EA. This EA need not be an ideal contained in dA, but it means D times this module. Okay. So what's the kernel? I claim that the kernel is EG inverse A. It's generated. It has to be a principal ideal, and the claim is that it's generated by EG inverse, where G is the GCD of D and E. So let's prove this. What does it mean for an X to belong to the kernel? It means that E divides DX. Not just E. That's the kernel of this map. X is in the kernel if and only if E divides X. But the kernel of this map is E need only divide dx. And E divides dx if and only if E G inverse divides X. Okay, so X is a multiple of EG inverse. In other words, the ideal is the one generated by EG inverse. That's what we needed to prove. And the next thing is, suppose I take the map from E to A modulo EA. And so it's the same as here, except that now I'm not asking for the kernel of the multiplication by D map on A modulo EA. I'm asking for the co-kernel. Yeah. What am I asking for? No, here is the co-kernel already. Yeah, so what is the map from A to the co-kernel? That's the question. And the answer is that it's GA. Yeah, exactly. So the co-kernel is being determined here. It's the co-kernel is canonically isomorphic to A modulo GA. So how do you prove that the kernel of this whole thing is equal to GA. Now, by definition, X belongs to the kernel if and only if X bar is equal to D times Y bar for some Y bar in A. So for some Y in A, right? The kernel of this map are multiples of D. That means that X minus dy is equal to Ez for some Z in A. And that means that X is in this ideal dA plus EA, which is actually GA, right? The definition of the GCD was that it's any generator of the ideal dA plus EA. The GCD of D and E is any generator of the ideal dA plus EA. Okay. And the final thing is that, goodness, yeah. So this is the analog of the Chinese remainder theorem that you might be familiar with in over the ring Z. But this is a result which is true for every principal ring. So, yeah, that's going to be a consequence of this. It says that the kernel, if I take the map from A to A modulo dA cross A modulo EA. Okay. What is the kernel of this pi? Pi is a map which takes A to A modulo dA cross A modulo EA. And the claim is that it's dA intersection EA. So this is again easy to prove. If X is in the kernel, if and only if, well, I mean, there's nothing to prove here actually. But the consequence is that the important thing is that if G is equal to 1, if the GCD of D and E is equal to 1, then pi is surjective. Why is it surjective? So if G is equal to 1, we can write dx plus EY equal to 1. And now let's look at the image of the element dx. Dx is certainly equal to 0 modulo D, and it has to be, what is it, modulo E. So modulo dx is equal to 1 minus EY, but EY is congruent to 0 modulo E. So dx is congruent to 1 modulo E. Similarly, pi of EY, what is that? EY is 1 minus dx. So it's dx is congruent to 0 modulo D. So EY is congruent to 1 modulo D. That's what I've written here. And EY is certainly congruent to 0 modulo E. So pi contains the images, the image of pi contains 0, 1 and 1, 0. But 0, 1 and 1, 0 actually generate this A module. So the image has to be the whole of A modulo D cross A modulo E. That's what it means to say that pi is surjective. Now you can also check that we know the kernel now, in general, and we know the image when the GCD is equal to 1. And you can check that if the GCD is equal to 1, this intersection, dA intersection EA, is also equal to dE times A. It's generated by dE, the product of these two ideals, so to speak. Okay? So what you get is a map from A modulo dE to A modulo D cross A modulo D, and it's an isomorphism, precisely when the GCD is equal to 1. Okay, so maybe this is the exact time to stop. I'm sorry that I have not been able to cover my other things. I'll have to take them up tomorrow, but this is a good time to stop. So let me just ask if people have any questions. Where is this thing? Where is the, I can't find the, oh, it has to be somewhere here. Yeah, here. Okay, so are there any questions? Somebody? Yeah? Dr. Priya Das, everybody is muted. All right. So if there are no questions, I'll sort of stop here today.
Thank you, sir. Thank you.
Oh, yes, I think they have no questions. So please clap for Professor Dalawat. Thank you so much, sir.
See you tomorrow then.
Yes, sir.